Okay, I think we're live. Let me just check the title. Yeah, title should be different. Okay, title updated. We are good. So, yeah, yesterday we finished chapter 9 with section where was discussion where to use panic or where to use result struct, and we started chapter 10 with intro, and today I'm gonna do section 10.1 generic data types. Yeah, but before the start I want to test something because yeah, thank Marcus, he reached me on Twitter and told that actually people can chat in my Twitch stream, so I think I fixed it, but I want to test it actually. So yeah. So yeah, create test account. And yeah, it works. And maybe check also if the YouTube stream forward the chat as well with Restream bot. Okay, somehow it's not works, but anyway, Twitch chat is working, so should be good. So let's back to our book and start with generic data types, where we use generic to create definition for items like function, signature, or structs, which we can then use with many different concrete data types. Let's first look at how to define functions, structs, and nums and methods using generics. Then we'll discuss how generics affect code performance. Okay. So in function definition, yeah, basically yesterday in the intro, let me switch here. So we use this code snippet where we reuse code with the function, and the next step supposed to be use generic to apply this logic for different data types. So I guess it's what will be discussed here now. When defining a function that uses generic, we place the generic in the signature of function, where we would usually specify the data types of the parameters and return value. Doing so makes our code more flexible and provides more functionality to the caller of our function while preventing code duplication. Continuing with our largest function, listing10for show how two functions that both find the largest value in a slice will then combine those into a single function that uses generic. So you see basically the same code, largest I32, largest char. This actually body of the function is identical, but because type are different, we can't use it for different types. So this is the problem we're gonna solve. The largest isolated function is one we extracted in listing10.3 that find the largest I32 in a slice. The largest chart functions find a largest chart in a slice. The function bodies have the same code, so let's eliminate the duplication by introducing generic type parameter in a single function. To parameterize the types in a new single function, we need to name the type parameter just as we do for the value parameters to a function. We can use any identifier as a type parameter name. Okay, but we'll use t because by convention type parameter names in Rust are short, often just a letter, and Rust type naming convention is camel case, short for type, letter T, capital K, camel case. The default choice of most Rust programs. Okay, so it's not necessary, but it's just a default choice. Like here, we can put any string, but yeah, T is what you probably will see most in the Rust code. When we use a parameter in the body of a function, we have to declare the parameter name in the signature so the compiler knows what the name means. Similarly, when we use a type parameter name in function signature, we have to declare the type parameter name before we use it. To define the generic largest function, place type name declarations inside the angle brackets between the name on the function and the parameter list like this. So this is where we define the generic and then we use it as a type here and here. Yeah, maybe let's just try to replace our previous implementation, and here we'll have capital T and its reference, right? Okay. Now it's not built because we don't know if T can do this operation, I guess. All right. We read this definition as the function largest is generic over some type T. This function has one parameter, sorry, parameter named list, which is slice of value of type T. The largest function will return a reference to value of the same type T. Okay. Listing 10.5 shows the combined largest function definition. Sorry, let me have a sip of water. Yeah, show the combined largest function definition using the generic data type in its signature. The listing also shows how we can call the function with either a slice of ICT2 values or char values. Note that this code won't compile yet, but we'll fix it later in this chapter. So yeah, this is look like kind of the same what we have. And let's try and just use it in a result in the main function. As it says, it won't work yet. So if we compile this code right now, we'll get this error. Binary operation bigger cannot be applied to type reference t. Consider restricting type parameter t std cmp partial ort. For more information, error explain could not compile chapter 10 due to previous error. So the help text mention std_cmp partial ort, which is a trait, and we are going to talk about trait in the next section. Yeah, 10.2. For now, note that this error states that the body of largest won't work for all possible types that t could be. Because we want to compare values of type t in a body, we can only use types whose values can be ordered. To enable comparison, the standard library has the std_cmp partial ort trait that can implement on types. See Appendix C for more on this trait. Okay. By following the help text suggestion, we restrict the types valid for t to only those that implement partial ort, and this example will compile because the standard library implements partial ort on both i32 and char. So basically, as I understand it, we should somehow tell that we won't use we are gonna use only types for t which implements this functionality. Basically compare, so we can compare item and largest. So in struct definitions, we can also define struct to use generic type parameter in one or more fields using the angle bracket syntax. Listing 10.6 define point. So wait a minute, so we're not gonna fix this yet. Yeah, I just don't get by following the help text suggestion, we restrict the type valid for t. Oh, we need just do it like this, right? Okay. And now we are fine. Or we can use no. I think I will skip this for now. Just wanted maybe try if I can use std cmp partial or and do it like this. Maybe try to run. Yeah, it works fine, and it works for i32 and for chart types. Okay. And code action also suggests feature move to where clause, so we can add where in the end and describe what t is restrictions. This is interesting. And yeah, it also works. So this is, I guess, alternative way to describe it. Here, maybe I might make it a bit readable. Okay, so we find this function. Now we can move to struct definitions. We can also define structs to use generic types parameter in one or more fields using angle bracket syntax. Listing 10 seek define the point struct to hold x and y coordinates value of any type. Yeah, let's quickly implement it. Struct point t and x t y, sorry, be t and y should be t, and now we can do let p1 like this, and also and maybe try to run it, even just build. So yeah, warning about unused variables, but it compiled fine. And you see, we don't need even specifically say what kind of point it is, because it calculated from the code here. But I think we can do, for example, if now it's i32, we can specifically say it's u8, for example. No. Oh, I did it wrong. It should be something like point u8. Yeah. So Rust can calculate what type it should be by itself, but Also, we can explicitly specify what it should be in case we need something else here. So the syntax for us using generic instruct definition is similar to that used in function definitions. First, we declare the name of the type parameter inside angle bracket just after the name of the struct. Then we use the generic type in the struct definition where we would otherwise specify concrete data types. Note that because we used only one generic type to define point t, this definition says that the point t struct is generic over some type t, and the field x and y are both the same type. Whatever the type might be, whatever the type might be. If we create an instance of point t that has value of different types, as in listing 10.7, our code won't compile. So if we place two different types, it will not work. And we can quickly test it. And you already see Rust analyze and complain about it. We also can do cargo build, and yeah, expected U8 found floating point number. In this example, when we're using the integer value of 5 to x, we let the compiler know that the generic type t will be an integer for the instance of point t. Then we will specify 4.0 for y, which we've defined to have the same type as x. We'll get a type mismatch error like this. Mismatched types, expected integer found floating point number. Yeah, exactly what we have. To define point struct where x and y are both generic but could have different types, we can use multiple generic types parameters. For example, in listing 10.8, we change the definition of point to be generic over type t and u, where x is of type t and y is of type u. All right. Yeah, we can quickly change it. So like this, and then we need to if we want to tell it explicitly, or if we want to find it automatically. So it's R32, U8, F32, F64. All right. So we can have more than one generics per each type we need. Now all the instances of the point shown are allowed. You can use as many generic type parameter in a definition as you want, but use more than a few makes your code hard to read. If you are finding you need lots of generic type in your code, it could indicate that your code needs restructuring into smaller pieces. Yeah, this is just some marks in your code, like when you have something written twice, you need to refactor, basically maybe put on a separate function. If you have a lot of generics, so in one place, maybe you just need to restruct your code and make it in small pieces. Just simple refactor rules. In enum definitions, as we did with struct, we can define enum to hold generic data types in their variants. Let's take another look at the option T and num that the standard library provides, which we used in chapter 6. So basically, yeah, option is take generic T and for value. And value basically can be any type, I guess. There's no specific restriction. Yeah, this is clear one. This definition should now make more sense to you. As you can see, the option T and num is generic over type T and has two variants, sum, which holds one value of type T, and non-variant that doesn't hold any value by using the option T and num. We can express the abstract concept of an optional value, and because option T is generic, we can use the abstraction no matter what the type of the option value is. Okay. Enum can use multiple generic type as well. The definition of the result enum that we used in chapter 9 is one example. So yeah, result have generics T and E, T for OK value and E for error value. The result enum is generic over two types T and E and has two variants OK, which holds a value of type T, and error, which holds the value of type E. This definition makes it convenient to use the result enum anywhere we have an operation that might succeed. Return a value of some type T or fail. Return an error of some type E. In fact, this is what we used to open a file in listing 9.3, where T was filled in with type stdfs file when the file was opened because when the file was opened successfully, and E was filled in with type stdio error when there were problems opening the file. Okay. When you recognize situation in your code with multiple struct or enum definition that differ only in the types of the value they hold, you can avoid duplication by using generic types instead. So yeah, another rule, if you have some duplication but only differ by type, you have to use generic. Completely makes sense. In method definitions, so we can implement methods on struct and enums as we did in chapter 5 and use generic type in their definition too. Listing 10.9 showed the point struct. We define it in listing 10.6 with a method name x implemented on it. So let's try. So info t point t f and x self reference to the t and return self x. Yeah, the problem is we have point with define it like this. And in this case we need, I guess, do it like this. And now we can do something like this cargo run, and you see p1.x equal 5. So yeah, works as expected. So we are good here. Here we defined a method named x on point t that return a reference to the data in the field x. So basically, I guess generics like struct point contain generics, and it should be identical here. Maybe not like identical, but maybe let's try rename it, for example, and use some. Yeah, it still works because it doesn't really matter what the name of the generic type. Let me run just to be clear. Okay, but we can do it like this, I guess, because we have to be sure it match this point and this point. Okay, so here we defined a method named x on point t that return reference to the data in the field x. Now that we have to decide t just after implement, so we can use t to specify that we are implementing methods on the type point t by declaring t as generic type after implementation. Rust can identify that the type in the angle bracket in a point is a generic type rather than a concrete type. We could have choose a different name for this generic parameter. Yeah, exactly, we tried. Then the generic parameter declared in the struct definition, but using the same name is conventional. Yeah, for sure it's preferable to have same names. Easier to read the code then. Method written within the implementation that declares the generic type will be defined on any instance of the type, no matter what concrete type ends up substituting for the generic type. So yeah, this method will work for any point, no matter what type it will be. Like, I guess we can do something like char here, and then do something like this. Yeah, and you see it works. All right. We can also specify constraint on generic type when defining method on the type. We could, for example, implement method only on point f32 instances rather than point t instances with any generic type. In listing 1010, we use the concrete type f32, meaning we don't declare any type after implementation. Let's try this one. So we have info point f32. Yeah, but I still want to have a... Okay, let's just do it like this. And to find distance from the origin, Yeah, that's what we're looking for. And now, can we try to do something like this? And we have an error. No method distance from origin on type point UF32. But if we do like this, and then yeah, I think now it should work. Cargo run. Yep, it works. This code means the type point f32 will have distance from the origin method. Other instances of point t where t is not of type f32 will not have this method defined. The method measures how far our point is from the point coordinate. It coordinates 0, 0 and uses mathematical operations that are available only for floating point types. Generic type parameters in struct definition aren't always the same as those you use in the same struct method signature. Listing 1011 uses the generic types x1 and y1 for the point struct and x2, y2 for the mix-up method signature to make the example clearer. The method creates a new point instance with x value from the self point of type x and the y value from the passed in point of type y2. Okay, let's take a look first. Basically looks like what we have already, so we can just say it's x1, this is y1, and this is again x1, and this is y1, and everything is the same. And then we can add this implementation. Mix up. So what happened here? So return. So we have 2 points with different types. Let's take I don't know, let's redo this one to be like this. And now we can do what it return? It returned the point, so let before, yeah, something like this. And in this case, we should have P for U8 F32. Okay, let's do it after the println, so we don't break the ownership. So yeah, we take X from self and Y from other. So we mix X1 with Y2, exactly as return type said. Maybe we can print yeah, it prints 5 and 10, but the 5 is actually U8 and 10 is F32. So in main we've defined a point that has an I32 for X with value 5 and F64 for Y with value 10.4. The P2 variable is a point struct that has string slice for X with value hello and a char for Y with value C. So yeah, I32, F64, and this is string and this is char. And end result here is X will be self, it's I32, and Y will be char. Yeah, exactly. And the purpose of this example is to demonstrate situation in which some generic parameters are declared with implementation and some are declared with the method definition. Here, the generic parameters x1 and y1 are declared after the implementation because they go with the struct definition. The generic parameters x2 and y2 are declared after a function mix-up because they're only relevant to the method. So yeah, basically the point is here. Those is belong to the struct, but x2, y2 is nothing about the struct, it's about the method or function here. Okay, and yeah, interesting topic, performance of the code using generics. Is it something wrong with performance? I wonder. I guess it should be not problematic, but yeah, let's take a look. You might be wondering whether there is a runtime cost when using generic type parameter. The good news is that using generic types won't make your program run any slower than it would be with concrete types. Yeah, this is what was my thought, and I was really wonder why there is a performance topic at all. Rust accomplished this by performing monomorphization of the code using generics at compile time. Monomorphization is the process of turning generic code into specific code by filling in the concrete type that are used when compiled. In this process, the compiler does the opposite of the step we use to concrete the generic function in listing 10.5. The compiler looks at all places where generic code is called and generates code for the concrete types, and the generic code is called with. So basically from the generic at compile time it look like this, even if we use generic here. All right. Let's look at how this works by using the standard library generic option t and num. Let integer sum 5 and let float sum 5.0. When Rust compiled this code, it performed monomorphization during the process. The compiler reads the value that have been used in option t instances and defines two kinds of option t. One is i32 and the other is f64. As such, it extends the generic definition of option t into definitions specialized to i32 and f64, thereby replacing the generic definition with the specific ones. Okay. The monomorphized version of code looks like to the following. The compiler uses different name than what we are using here for illustration. So instead of creating two enums, option i32, option f64, and yeah, this is will look like this and look like this from the our code in our RC files, and this what something like this will be generated code for compiler. The generic option t is replaced with the specific definition created by the compiler. Because the Rust compiled generic code into code that specifies the type in each instance, we pay no runtime cost for using generics. Okay. Yeah, so basically it's code with generics regenerated into code without generic, so there is no cost in runtime. Basically simple like this. When the code runs, it performs just as it would if we had duplicated each definition by hand. The process of monomorphization makes Rust generics extremely efficient at runtime. Okay. So this was generic data types section. Next one is the trade, and really interesting, and I'm excited about it, but yeah, this looks like a big one section, so I'm not going to start it today. We'll jump on it on the next stream. But what I can do, I would like to play a bit with Rustlings exercises. So yeah, let me move my camera. Something like this. So we finished with move semantics last time exercises, and what is structs next one. So structs 1.rc. And what is the exercise here? Address all the to-dos to make the test pass. Okay, so to do here, something goes here. Color classic struct. Okay, so if we take a look here, we expect it would be struct with red, green, blue. So red, yeah, just like this. Blue 8 and green. And also color plus extract. I think we resolved this one, but oh yeah. But then there is a union. So is it supposed to be struct? Interesting. So and some to do here. This is the tuple. So color. Unit like struct. What is the unit like struct? To do So let's quickly back to the structs, data types maybe. Okay, structs, defining structs and unit like structs. Okay, yeah, this is something I was thinking about. Oh, we already have it. I missed just this one. So we just need to do unit. Is it like this? And what is the name? The name actually. Yeah, we are done here. So I'm not done. We remove this and going to the next example. Sorry, exercise. So the task here address all the to-dos to make the tests pass. Okay, so to do, create your own order using the update syntax and template above. So let your order, okay, order template. Create update syntax. What is update syntax? Okay, what we expected. Your order name. Okay, I think I get. We just going to create order. And name will be order template name. Oh, we maybe can just do something like this. Yeah, I guess some fields are different. So order count. The name hacker in Rust. Her name will be okay. We need a string, so to string here. Panicked at assertion file left equal right. Line 48. So count 1. Order has no field name. Oh, yeah, there is a typo. Yay, we're done. Yeah, we read about it and it wasn't too hard, but without practice, you see, it takes time to understand all this terminology. So it's really useful to practice a bit with this actually simple rustling exercises, but they make sense. So let's read. Structs contain data, but can also have logic. In this exercise, we have defined the package struct and we want to test some logic attached to it. Make the code compile and the tests pass. Okay. So let's start with tests. Let's take a look. Struct 3RC line 29. Line 29 is international. So package is international and the package is the sender country and recipient country. So I guess we want to return boolean here, and we want to compare self sender and recipient country. So is it still? No, I think it's different now. So get fees. Get fees cent per gram. So it returns I32, I guess, and weight in grams. Okay, so we basically need just multiply self Weight weight in grams on cents per gram. And yeah, we are good here. And we're done with structs. What next is the enums. Maybe let's quickly take a look in the enums. Just for exercise. Yeah, I think we will do it, and that's it for today. So define a few types of message as used below. So I guess we can do it just like this. Now execute. Yeah, to do is define the different variants used below. So again, remove echo. Yeah, let's just copy this part from previous exercise, and now move supposed to be, yeah, like this. And the change color, and echo is string, I guess. Yep, we are good. And what is to do here? Implement the message variant types based on their usage below. So message, what is the usage? Change color. It looks the same. We have it here, so let's just copy paste it. Let's take a look what is next to the process. Okay. We do a process, and on the line 62, so we have state. Oh, okay. The state process, and we have to update so self Why textually complain on line 32? And this is not a value. Message move point. Yeah, to be honest, I don't really understand what the error says. So the color, can we do okay, we can do match. Let's match message, right? State you true. So message echo string, then self echo. I don't know, something like this. Then message move, self move position, and message change color. So something wrong with the did we define the point? Yeah. Oh, I see. The type is different. So I guess yeah, actually we don't need this one, and we just should use point here, I guess. And yeah, we are good. So this is the was last for enums, and next will be strings. I think it will be more interesting if we will use if I turn off Copilot for these exercises. I do a bit spoilering for me. So yeah, so exercise is not as effective. It's easier to pass each exercise, but I guess not as good in the end of the day. So yeah, thank you everyone for watching. We'll see you next stream, maybe tomorrow.